I'm Steve Austin. I'm a geologist. I've been interested in northern Arizona and studying the landscape out there. And I'd like to talk to you today about the shoreline terraces mark the western margin of ancient Hopi Lake, Arizona. And I'm one of 7 authors also associated with this paper that was given at the Creation Research Society meeting in August of 2024 is 𝘎𝘕𝘯𝘴 𝘏𝘪𝘴. He's a physicist by training, worked on cloud seeding technology, and he is very experienced with digital elevation modeling, and DEM for short. And then Thomas Folks. Thomas Folks is a BLM land manager in northern Arizona and is experienced with government regulations and permitting and that type of thing, and permissions to go visit some very interesting areas, Indian sensitive, that type of thing. Joseph Austin is my brother, younger brother, and he's a geophysicist by training, and he is experienced with ground penetrating radar, and so he helped study the landforms in the desert using ground penetrating radar. J. Peter Vanko is an architect, but he is a precision surveyor, and his DJI Mavic software, he's able to map very exactly the terrains that we're interested in. And then Nathan Mook is a engineer by training, geological engineer, and he loves digging trenches. And so one of the primary things that we do as geologists is dig trenches to study soil thickness and that type of thing. And he is a marvelous trench digger and interpreter. And then Nate Loper. Nate Loper is involved with teaching in northern Arizona, based out of Flagstaff, and he runs Canyon Ministries. And so together we make a good team to study the shoreline terraces that mark the western boundary of ancient Hopi Lake. And in the image here, you can see Grand Canyon. There's what eastern Grand Canyon. Here is this giant basinal structure called 𝘎𝘠𝘃 Basin, and we've simulated a 5,800 feet elevation lake in that basin, and then you're looking off into southern Utah and southern Colorado, and you can kind of see the terrain here. That lake is about 1,000 cubic miles in volume. It's a huge terrain. I'm going to ask the question, did Hopi Lake fill 𝘎𝘠𝘃 Basin? Notice 𝘎𝘠𝘃 Basin is a huge terrain, even in the continental scale image. You can see this enormous basin, and that red dot is the 25 square kilometer tract that we're studying in detail in this presentation. We're going to study the landforms at 1,700 feet, or pardon me, 1,700 meter elevation, and that's 5,740 feet elevation. So that's a high elevation lake that we're going to suggest in that basin. And then we're going to talk about the geologic cross-section through the terrain and what that says about our understanding of the landforms. And then I'll talk about the ground penetrating radar, and then I'll go to the encrusting tufa. Tufa is a kind of a bathtub ring often left by lake, and so we're going to be looking for tufa deposits, the bathtub ring essentially of the lake. And then I'm going to talk about landforms that are shoreline terraces. In other words, they're features that were left at the margin of the lake. And then I'm going to talk a little bit about top-down spillover model and the failing of the lake and its relationship to Grand Canyon. 𝘎𝘪𝘶𝘃 Basin is that enormous basin. Shaded relief map of Northern America shows it really well. And so can you imagine Lake Michigan-sized lake in that basin? Was 𝘎𝘪𝘶𝘃 Basin the holding pond for ancient Hopi Lake? And do shoreline terraces exist for Hopi Lake? That's the science questions that we're asking here. And this would be a lake before the Grand Canyon was eroded. The lake can't exist today with the present terrain of Grand Canyon. So it starts getting interesting. The simulated lake is up against Grand Canyon, which wasn't there when the lake was there, and we proposed the lake was at about 5,800 feet, 1,760 meters elevation. And so that lake, we believe, failed through the uplifted terrain and on the west side. There's a supersonic fly-through. Just in a matter of seconds, you're going the length of Lake Michigan, all across the terrain. You can see the lake, but it couldn't exist today because the Grand Canyon is there. But what if the Grand Canyon wasn't there? It could be involved with the erosion of Grand Canyon. Here's the research area that we're fascinated by. It's 25 square kilometers in area. It's a box that's 5 kilometers by 5 kilometers, north-south oriented kind of box. And it's on the western side of 𝘎𝘪𝘶𝘃 Basin, which would make it the western side of ancient Hopi Lake. Little closer detail, there's our 25 square kilometer box. Okay, there's some interesting terrain with faults running through there. Our field research area is a limestone ramp that extends from Flagstaff, Arizona up here down to the east and creates this interesting terrain. It's a limestone ramp. More detail of the area. It's between Flagstaff, Arizona and Winslow and other areas down here. The box is along Interstate Highway 40. There's Interstate Highway 40. There's Canyon Diablo, which is a drainage that extends to Meteor Crater, Arizona. Our area is about 20 kilometers away from Meteor Crater, Arizona. Here it is sitting. Anderson Canyon, Wagon Box Draw, Elliott Canyon are tributary to Canyon Diablo, which is tributary to the Little Colorado River. That's the 𝘎𝘪𝘶𝘃 Basin terrain that we're looking at in the high country in northern Arizona. We have a bedrock ridge that I want to talk about, and that's what we're going to spend the time talking about is bedrock ridges. Now, as we draw back, you can see this ridge of limestone that runs across this image, but you'll see it's part of an enormous field of landforms that make this very unusual terrain. Bedrock ridges, and we call it Chevron Hill. That's one of the hills on the northern side of the 25 square kilometer tract. And now you're seeing these bedrock ridges. We use the word bedrock ridges because we have no other term to describe them originally, so we just call them bedrock ridges. But they're linear, they're spaced about 20 meters apart, and they're stair steps on the side of the hill. And they curve around and have, even though they're parallel, they take turns. You can see the truck up there. That's the field research vehicle that we're using out here to do this terrain. The whole terrain is 25 square kilometers. 25 square kilometers, and we have a kind of an orientation map showing the areas that are specific interest. But the 25 square kilometer elevation is area is about 1,750 meters elevation. It's studied by DEM, Digital Elevation Model overlay displays, and this just general 2-meter contour interval map of the 25 square kilometers. I'll talk about this area up here, Interstate Highway Arch along Interstate 40. I'll talk about Chevron Hill, and we saw the image of Chevron Hill, the bedrock ridges, already on that image before. And I'll talk specifically about Nates Hill, and we'll take a brief survey of the features of Nates Hill. We used DJI Terra software to map in detail the 25 square kilometer area. DJI software using tens of thousands of overlapping images. Where the images overlap each other in detail with a different trajectory of the flight of the UAV that is taking all these photos, that the tracks have resolution up to 3 centimeters resolution, and on especially 3 areas: Chevron Hill, Nates Hill, and the GPR, ground penetrating radar site, which is adjacent to Nates Hill. And the overall terrain is mapped with a resolution, ground surface distance resolution of about 10.8 centimeters. So these images can be resolved down to incredible resolution. And the whole resolution of the 25 square kilometer area has to be billions of pixels. Okay, so it's it makes old ways of mapping go extinct because of the DEM and the high resolution of the DJI Terra software. We use the word bedrock ridges to describe those parallel ridges that are at an elevation of about 1,700 meters. And they're parallel, often about 20 meters spacing, and then they have horizontality. They conform generally to the horizon and to fold structures. Horizontally, the elevations deviate, and horizontality deviates near faults, and I'll talk about that. And then stair-step morphology. As you go from one bedrock ridge to the adjacent bedrock ridge, there'll be a change in elevation. And that stair-step morphology is called a terrace, right? So we could be more specific and call the bedrock ridges terraces. And then their dip slope outcrop along the Kaibab limestone. We'll talk about what the field evidence there is, and flats with locally derived limestone gravels. There's a tufa incrustation, abundant and often very thin, and it's interpreted as transgressive shoreline terraces. That's where we'll go with the bedrock ridges. Here you see Interstate Highway 40, and then you see the display at the north end that's called Interstate Highway Arch, and it's a plunging anticline, and this plunging anticline has around its slope those bedrock ridges. And so that's showing you the amazing horizontality associated with those, whatever those structures are. This is where interstate highway engineers quarried the gravel off the top of the bedrock ridges, used that gravel to make the interstate highway. So you can see some of the interesting things that are there. Nates Hill. Nates Hill is also very interesting, and you can see here the slope to the south, and you can see the 2-meter contour intervals, and you see the bedrock ridges. They are amazingly horizontal over a large part of Nates Hill. And then as you go off to the northeast, you see something happen. The horizontality of the ridges deviates strongly from the present horizontal position, and the lines, the contour lines deviate. And so what is that showing? It's a fault scarp, and we're looking at a fault scarp, and we're seeing a horizontal displacement along the fault, and this area adjacent to the fault has been altered by the fault, and that's called drag, the effect of drag on the fault. And so Nates Hill shows not only the horizontality of the ridges generally, but then it shows the deviation from horizontality in a very believable way. Drag on what's called a listric normal fault. Graben Hill on the other side of this fault area, it shows again ridges following contour line, and then you can see the contour lines deviate from the directions of the ridges. And so this is a trough, a graben structure, and the down-faulted strata here in the graben create drag on the fault, and that causes deviation from the horizontality of the ridges. That argues that the ridges are older than the fault, essentially. And here you see the fault scarp and the overlook of Nates Hill looking south, from the north looking south, and you can see Buffalo Range Road, the road into the field research area. You can see the graben structure between the two faults. There's a fault over here and the fault over there, and the fault scarp really creates a strong contrast between the 𝘎𝘬𝘃𝘃 formation, the red mudstone, and the light gray limestone of the Kaibab formation. And then you see wagon box draw syncline, and then you see a dip slope with bedrock ridges, and then you have Nates Hill anticline with 𝘎𝘬𝘃𝘃 formation, and then the formations in the bottom of the image here dip to the north. And there's petroglyph rock. We'll go see that in more detail. There's the GPR, ground penetrating radar transect, and you see an old fence line and road that goes along the cattle country that's out there. Okay, I'm going to fly over fly over the terrain toward the tank. That's called wagon box draw tank, and that's a rancher's structure, landform built for ponding of water for cattle. But then you see the syncline, you see the bedrock ridges, and then you see, when you see 𝘎𝘠𝘃𝘃 Formation, you don't see very much in the way of bedrock ridges all the way up there to the 𝘎𝘠𝘃𝘃, well exposed on petroglyph rock. You can see the 𝘎𝘠𝘃𝘃 down in the syncline, or in the trough structure, and you see there's the fault scarp, technically. Okay, take a look at the flyover, and it gives you the perspective of the various features that we're looking at. You see petroglyph rock there in the corner, and then as you fly south, you see the fault scarp, and then you see the bedrock ridges on the terrain. And then as you look off in the background, you can see the tank structure, and that allows us to create a cross section of the syncline and anticline structure. There's the bedrock ridges. Very important to see the contrast between the Kaibab Formation, the gray Kaibab limestone, and then the overlaying 𝘎𝘠𝘃𝘃. Here's a 𝘎𝘠𝘃𝘃 mudstone, and there's 𝘎𝘠𝘃 sandstone. And then you're looking off, there's a little bit of ridged terrain on the syncline here. Here's the tank, wagon box tank. Here's the overflight image. You can see of Nate's Hill, and you can see the cross section we can draw through Nate's Hill of the relevant landforms. And off to the corner on the side here is the GPR, ground penetrating radar site. So we're gonna look for this, the cross section. And there is very beautifully preserved on petroglyph rock, the 𝘎𝘠𝘃𝘃 mudstone, only about 3 meters thick. And then on top of that, the 𝘎𝘠𝘃𝘃 sandstone. And then all around it, you can see the gray rock of the Kaibab Formation. Nate's Hill geologic cross section, you can see it. The blue arrows point to obvious locations where along the cross section we can exactly specify what the predicted Kaibab 𝘎𝘠𝘃𝘃 boundary is, and then we can use software to fit the curve and describe the anticline, syncline structure, and the dip slope occurs along the cross section. Here's petroglyph rock, about 1,720 meters elevation. Here's the anticline, okay, northward dipping strata, level strata, and then here's the dip slope, and there's the syncline over there by wagon box tank. So the topographic profile. What are these linear landforms doing on this limestone dip slope at 5,700 feet elevation? See the landforms? They're on a dip slope of the upper part of the Kaibab Formation and the limestone. that forms Nate's Hill. So the upper part of the strata are exposed, and it's showing the bedrock ridges, but it can't be individual beds of limestone because it's a dip slope, and that shows the very obvious conclusion that they're not bedrock individual limestone layers on the bedrock ridge. This is the ground penetrating radar site, and here's where we take a look at the ground penetrating radar. But there's a 130 meter long trail that we made over the landscape, showing the bedrock ridge, crossing the bedrock ridges with the elevation contours. And these are 10 meters wide. And here you see 4 people standing there. 1, 2, 3, 4 people were casting a shadow over the landscape, and we're seeing the terrain drop off to the south. The ground penetrating radar shows the image of the gravel and bedrock underneath the trail, and it creates this amazing interpretation. So we have very thin gravel, actually usually less than a meter thick gravel deposit between the bedrock ridges, and the bedrock ridges are dip slopes of limestone. And you can see the layered limestone dip slope, and so they're not in multiple beds of limestone, they're one image. Okay, and so the gravel strewn flats. Here we are, we've dug a couple of trenches through the terrain. And because the gravel is thin, we can measure the gravel thickness directly just by digging trenches. And so that's what we've done. It's hard to dig a trench along hole 20, a whole distance of 130 meters, but you see the what it must be like from the ground penetrating radar. So we're asking the question, is this beach deposition and beach deposits? And that's a very important question. We're looking at the terrain, and what do we see? A whole bunch of blade-like objects of limestone laying on this surface. And it kind of looks like a beach because you see tablet-like pebbles, especially along a beach. And so could that be the beach ridge? And it looks like it's covered with a coating of some type. And then we see the orientation of the horizontality of the ridge compared to the gravel around the ridge. And so we ask, is this beach deposition? And that kind of is an obvious first question you want to ask. Does it look like a beach? It does. Okay. There's a flat area with gravel underneath. Then there's the face of the landform. Then there's the high point of the landform, which is the berm. And then there's the next flat up a little bit, half a meter to a quarter meter higher elevation. And so this shows what appears to be the general landform. And the landform is encrusted with a substance called tufa. You see the normal gray color of the Kaibab Formation, then you see the yellowish brown, tan kind of image of the incrustation, the tufa. And you see here the cross section of the limestone, and then you see the tufa covering. Typically, 2 centimeters thick is the thickness of the Tufa deposit. Could that be the bathtub ring of the lake? Okay, and mineral deposition, calcium carbonate, could make this. Here's the flashlight microscope view of the spongy capping tufa, Buffalo Range Road area, wagon box draw. And as you see it, you see silt-sized calcite particles cemented by microcrystalline calcite and around a hole that's obviously the buildup structure of this chemical deposit. The strontium isotopes were studied. We studied the strontium isotopes in Bonneville, Lake Bonneville, Tufa. That's an Ice Age lake in Utah. We studied the Hopi Lake Tufa, and we studied the strontium isotopes in Kaibab limestone and travertine deposits of some of the cinder cones. And we notice immediately that Hopi Lake has its own Tufa signature of about 0.909 ratio of strontium-87 to strontium-86. So the strontium isotopes give us a signature that's completely unique to itself. And what is it like? The Hopi Lake Tufa deposit is very much similar to the upper drainage basin of the Colorado River. The upper drainage basin argues for what? That's the lake's strontium ratio. It's unlike the Kaibab limestone. It's unlike the modern Bonneville Tufa deposits. And so that leads to this model of a transgressive shoreline. You can see at 4 different horizons, the lake is rising, and as it rises, it creates landforms, the erosional scarp, inflection line, gravel-covered flats. And this structure appears to be a landform from transgressing lake shore, not a retreating lake, but a lake increasing in elevation. And so, we're looking at dip slope topography. So the resistant, friable, resistant, you can imagine the landforms created not by individual outcropping beds, but by maybe a resistant bed with friable beds located around it. So these depositional terraces can form in sequence by the rise of a lake. That's the good way to think about it. And of course, as the lake rises, the wave action becomes dampened. And so when the velocity depth profile, that shows you how the lake spends its erosional energy in wave erosion, creating the feature. These linear landforms cannot be erosional outcrop expression of multiple flat strata. Disproven by just looking at images of the fault scarp and the landforms, or back there studying the ground penetrating radar imagery. It cannot be erosional outcrop expression of multiple flat strata. Therefore, it has to be a landform inscribed some other way. Linear ridge-like and horizontal landforms on limestone dip slope at 5,740 feet elevation, are transgressive shoreline depositional terraces from rapid filling of ancient Hopi Lake. So Hopi Lake shoreline evidence is right in front of us, and seems to be the only sensible interpretation. So 𝘎𝘪𝘴𝘵𝘰𝘳𝘺 Basin, originally vacant of a big lake, you can imagine that. There wasn't a lake, and then somehow upstream drainage structure fails, probably from the top down, and that creates a lake in 𝘎𝘪𝘴𝘵 Basin. So we might look to the other basins upstream of 𝘎𝘪𝘴𝘵 Basin to see how those lakes could have failed. And so upstream basin structure fails from top down, and then Canyonlands Lake north of probably fails into 𝘎𝘪𝘴𝘵 Basin, creating this lake, Hopi Lake. And then the 𝘎𝘪𝘴𝘵 Basin fills progressively. The transgressive depositional terraces are produced on the southwest shore of the lake at 5,700 feet elevation. Hopi Lake fills, I think, to a final elevation of about 1,860 meters, about 6,100 feet elevation is the likely highest elevation that it reached in the present topography. And then the lake fails by spillover of Kaibab upwarp, the upwarp zone in northern Arizona that around Grand Canyon. And the spillway erosion of Grand Canyon begins by failing of the lake, and then the filling of Lake 𝘎𝘪𝑚 downstream at about 1,770 feet. That's about 5,800 feet elevation. And 𝘎𝘪𝑚 fails at 𝘎𝘪𝑚 Point, and so you can imagine a continual deepening and enlarging of the Grand Canyon by the continued spillover failure of these natural dams and drainage of the lakes. So this is a simulation of how erosion might occur. Animation of Hopi Lake spillover erosion. So we imagine a lake up in Utah, the big Utah lake. I call it Canyonlands Lake, and it breaches right here between Paria Plateau and Kaibito Plateau. It breaches right here and creates the first filling of 𝘎𝘪𝘴𝘵 Basin. So the breach, and that's at a place called Lee's Ferry, Arizona. Lee's Ferry, Arizona, the breach occurs. You can kind of imagine how that breach of that lake drains into 𝘎𝘪𝘴𝘵 Basin, filling 𝘎𝘪𝘴𝘵 Basin progressively, first an upper lake against Blue Moon Bench, and then a lower, larger body lake below. And then those fill the lake basin, and then the drainage across where the Grand Canyon is now creates a channel for the Grand Canyon. And it's about 5,800 feet elevation going into this other lake area to the west. That's 𝘎𝘪𝑚 Lake. And then 𝘎𝘪𝑚 Lake fails at 𝘎𝘪𝑚, and as it progressively drains, it creates more of the downcutting of Grand Canyon and, of course, Kanab Creek and Havasu Creek, and it creates the ultimately the whole drainage of the for the formation of Grand Canyon. Now let me run it again. Okay, here we go. The progressive drainage. As it drains between the low point between the plateau, and it creates Marble Canyon here, and the upper drainage basin above Blue Moon Bench, and then the lower drainage basin is filled, and 𝘎𝘠𝘶𝘮 Basin becomes a huge lake at about 6,100 feet elevation, and it loses about 300 feet elevation going down as it fills 𝘎𝘠𝘶𝘮 Basin, and it forms that basin. And as it fills that basin to about 5,700 feet, only a couple hundred feet of Grand Canyon has been eroded, but you can see the development of what is called Nick Point Retreat. As this lake drains, 𝘎𝘠𝘶𝘮 drains, it creates a nick point that retreats up the Grand Canyon and deepens the Grand Canyon, and then the side canyons form by a process called sapping structure. And so Nick Point Retreat associated with sapping structures are the ultimate evidences of this erosion of Grand Canyon, and the side canyons like Havasu Canyon and Kanab Creek Canyon. So let's go through it. Now you see the lake in Utah, the big southern Utah lake, drains between the two plateaus, and it forms Marble Canyon, which is associated with Lee's Ferry, which hasn't even been developed till the final drainage. But that's and you can imagine a nick point retreating up through the Paria-Kaibabito Plateau. And then you see the drainage here of Hopi Lake through the barrier of 𝘎𝘠𝘶𝘮 Basin, that's the plateau, the Kaibab Plateau, and it erodes down a spillway just a few hundred feet deep, but it's establishing the drainage channel. And then what happens at 5,800 feet, the canyon is basically formed between 6,100 feet and 5,800 feet. Then the lakes drain, and then what happens? The wet rock is exposed as the nick point retreats up to the old lake, and then it creates the sapping process, the process of failure of the side canyons, like Kanab Creek and Havasu Creek. And so nick points retreat up the slope and deviate into side canyons and then generate sapping process. I think that kind of explains how, in somewhat of a detail, the canyons form. So Hopi Lake legacy lives. The Hopi Lake legacy lives. Landforms are shoreline transgressive depositional terraces with gravel deposits on them and with shoreline tufa deposits. The terraces conform to the old slope of the basin ramp, and the transgressive tufa-encrusted landforms indicate rapid filling and then failing of Hopi Lake. Hopi Lake didn't take millions of years to drain, it was gone. And then top-down spillover model explains the erosion of Grand Canyon, especially the evidence of nick point retreat and sapping structures, the drying out of the sediment and the way it was cut. So that's the paper. Shoreline terraces mark the western margin of ancient Hopi Lake, Arizona. And I hope you enjoyed and profited from the detailed geologic survey and geophysical survey of the landforms there in northern Arizona. Thank you.